So far we have been discussing about the basic metric analysis of complex networks, and then we have also looked into social network properties. Now we will see into a little bit more algorithmic methods, okay, especially related to what we call community detection. Community detection, or sometimes also called analysis, community analysis. So, the basic idea is, given a graph structure, you want to find out dense subgraphs which are very tightly connected among each other, but are sparsely connected to the rest of the network. So, these modules actually, if you can efficiently extract these modules, then they are found to be very effective in various application designs later on. So, many unsupervised algorithms in machine learning actually depend on community or clustering as a first step. Okay. So, basically the point that I am trying to make is that given a graph structure, if you can identify these dense submodules very efficiently, then you can enhance the performance of various machine learning related applications to a large extent, okay, because many of these learning algorithms actually depend on the clustering as its input, on the input clusters. Okay. So, and the better the clustering algorithm, the more efficient will your application or your machine learning application be. Okay. So, in order to do this, the first thing that we need to do is to define what a community is. Now, as you can well understand that it is a very ill defined concept. Okay. There is no hard and fast or straightforward definition of what a community is. Okay. So, it is mostly, the concept is mostly philosophical if you wish. Okay. So, but then if you have to do certain application development, if you have to write algorithms to identify communities, then you have to somehow quantify this philosophical notion. And one very well accepted form of definition is that, if you look at these slides, is that it is a group of nodes that are densely connected amongst themselves while being sparsely connected to the rest of the network. So, for instance, let us take this example here. So, this set of blue nodes here, which I have circled by a red circle, they seem to be densely connected. Similarly, there is this set which is again densely connected, and also this set which is densely connected, but then there are sparse connections in between these densely connected submodules. So, basically each of this can be thought of as a community. Okay. So, and then these communities are sparsely connected by a very few edges. Okay. So, now the question is like how to go about and design efficient algorithms to extract such communities given large social graphs. For example, the communities in a Facebook graph or communities in a Flickr social network. Okay. So, here you have, so for instance, in Facebook you have, probably all of you have seen, there are various communities like social computing, communities like transition in social computing. So, these are all communities about social computing, whereas in Flickr you have similar communities like Enjoy Life, Baby's Life, Pond Life. Okay. So, all communities related to life. So, you can have such communities in various social networks. Okay. Now, the point is like how, given a set of nodes and a bunch of connections between this set of nodes, how one can efficiently design algorithms in order to find out meaningful community structures, meaningful substructures in this graph. Okay. So, and the problem might not be always very easy. For instance, if you look at the left hand side graph in this slide, the communities are very nicely well marked and well separated. Each color here would represent, you can immediately see that each color in this graph would represent a separate community. Whereas, if you look at the right hand side graph, it is not so easy to just look at the graph and tell what are the important communities hidden in this graph. So, and as and when the graph structure grows, Okay, it is more and more, it becomes more and more difficult to identify submodules just by looking at the graphs. Okay, so looking at the graphs, it is not always easy to identify or infer the densely connected submodules. So therefore, you should have some computational techniques, some algorithmic approaches to handle this problem. Okay. And in order to do that, the computational methods that people have suggested in the literature actually can be classified into at least 3 different types. The first one is called the agglomerative approach. The second one is called the divisive or bisection approach, and the third one is called the spectral approach. So there can be various other variants of these approaches, but roughly these are the kind of the 3, you can say, the pillars of computational techniques that you find in this area. Okay. So the agglomerative methods are one of the earliest methods for community detection or clustering. What you do is you make an empty graph, you have n nodes and 0 edges. Okay. And it is a bottom up approach. So at every iteration you kind of add edges between nodes that are most similar. Okay. And you keep on agglomerating in this way. So that is what is called the agglomerative approach, whereas the divisive approach is the other side of the coin, where you have the whole graph given to you, you find out the most probable edge that should be removed from the graph, okay, to divide the graph into 2 parts. Okay. And in this way you keep on removing again and again repeatedly the most probable edges until and unless the graph gets segregated into smaller dense components. Okay. And the third approach is the spectral approach, where you actually resort to the eigenvector analysis, eigenvector space analysis in order to identify communities. We will get to know more about this when we talk about spectral clustering. So as we will see there, that the second eigenvector actually contains important information about the community structure or the components or the dense connected components in a graph. So we shall see that when we deal more in details with the spectral bisection method. So the first thing that one needs to actually think about or ponder about when designing a clustering algorithm is the similarity or a dissimilarity metric, based on which you are going to, say for instance, you are trying to do agglomerative clustering. So you start with all nodes in separate clusters. Okay. Every node is in a single cluster. Now you have to, based on some similarity measure, actually establish links between nodes, and in this way you slowly grow up the cluster structure or the community structure. Now for this you have to, first of all, the first and the foremost task that needs to be solved is to identify a way to define similarity between a pair of nodes in a graph. So and there could be various different ways actually in order to do this. There is no one single sacrosanct way in which you can actually define the similarity between a pair of nodes. So basically that is why people often say that clustering is actually more of an art than of a science. Okay. Because this design of similarity measure actually is in many cases more important than the algorithm that you are using, okay, in order to do the clustering. The design of the similarity function, okay, is more important in many cases than the algorithm itself. So this is something that cannot be overlooked in the first place. This is one of the most crucial steps in devising a clustering algorithm or a community detection algorithm. Okay. So you can have various different measures. So some of the ways you can some of the ways we have already looked into. For instance, you can think of that 2 nodes are similar if they are structurally equivalent. So and we have looked into various notions of defining the extent of structural similarity in a graph, and you can say you can use any one of these measures to quantify the notion of similarity between a pair of nodes. So, in such ways, so not only structural similarity, you can use a lot of other different methods, say for instance just the number of common neighbors between them, or say the assortativity, the mixing coefficient that we talked about. So, if both of them are rich, they should be placed in the same community. So, the mixing parameter between them. So, all these different factors can be used to model your similarity function, to model the similarity function that you will use in order to put nodes within a cluster, call them similar to each other. Okay. So, in a nutshell, agglomerative methods actually can be divided into 3 steps. It is actually a 3 steps process, as you see in the slides. The first step is that you start with every data point in a separate cluster. Okay. Each and every data points, if there are n data points, n nodes in the graph, then you start with n different clusters. Now, keep merging the most similar pair of data points or clusters, okay, until you have one big cluster where you have all the nodes, where you have taken all the nodes together. So, at every step what you do, you merge a pair of nodes or one cluster with a node or 2 clusters, okay, and you keep iteratively doing this until and unless you have one big cluster which actually contains all the nodes in the graph. So, this is actually a bottom up agglomerative method. It's a bottom up fashion. So, you grow from the bottom. So, you look into pairwise cluster distances, and then based on it you actually merge the most similar clusters. Okay. And while doing so, you can generate something called a dendogram. So, this dendogram actually gives you an idea. Whenever you look at this dendogram, you actually get an idea of which clusters are most similar to one another and at what stage the 2 clusters have joined. So, for instance, if you look at this slide here, you see that there are a bunch of clusters that we can see, okay, and say there are nodes numbered from 1 to 16. The first 2 nodes, the height of the bars in this dendogram actually represents how close the 2 items are. So, you see immediately by looking at the dendogram, you can infer that nodes 1 and 2 are most similar because they have the least height. So, they actually join first, then the nodes 3 and 4 join together, then the nodes 5 and 6 join together, then in similar fashion 7, 8, 9, 10, and then after a certain point in time there are clusters who say 5 and 6 and 11 and 12 join together at this particular point. So, the height of this line actually shows the point of iteration in the iterative agglomerative algorithm where the 2 clusters have actually joined to form a new cluster. Okay. So, in this way, so basically you have smaller clusters in an earlier stage of the iteration which actually join to form larger clusters until and unless you have one single cluster at the end of the full execution of the algorithm. Okay. So, now we have been continuously talking of the idea that 2 clusters need to be joined based on their similarity. Okay. So, you can estimate the similarity between a pair of nodes by some similarity function, but the question is how to estimate the similarity between a pair of clusters or say one cluster and a node. Say for instance, if you have 2 clusters C1 and C2 here and say C3 here. So, now in the next iteration, which are the 2 clusters that you should merge? So, you have to define somehow a similarity notion between all pair of clusters, or say you have 2 clusters C1, C2 and a node X. So, now in the next iteration, whether X combines with C1 or X combines with C2 or C1 and C2 combines, okay, has to be decided. Now, this has to be decided based on some sort of similarity notion between C1 and X or C2 and X or C1 and C2, right. So, this idea is called actually the idea of linkage, and again as you can imagine there could be various ways of defining the similarity between a pair of clusters or a node and a cluster. So, if you can define the similarity between a pair of clusters, that automatically you can see that automatically translated get translated to a similarity between a single node and a cluster. Okay. So, if you somehow can define the similarity between two clusters, say C1 and C2, then automatically the notion of similarity between one single node and the cluster is also defined, because you can imagine that C2 is just consisting of one single node. Okay. So, then the idea is that you have to somehow define the similarity notion between a pair of clusters. Now, in order to do that, we come up with the idea of linkages, and there could be at least 3 different forms of linkages. The first form is called single linkage. The second one is called complete linkage. And the third one is called average linkage. So, in the single linkage idea, what you do is that the distance between the clusters, is set to the minimum distance between all pairs, okay, across the two clusters. This distance between clusters is equal to the minimum distance between the contents or the data points between the all pair contents or data points across the two clusters. So, basically what we mean, say for instance, if you have two clusters C1 and C2 and there are data points x1, x2, x3 and x4 here, and there are data points y1, y2 and y3 here. So, you find out pairwise distance between x1 y1, x1 y2, x1 y3, x2 y2, x2 y3, x2 y1, x3 y1, x3 y2, x3 y3. Similarly, x4 y1, x4 y2, x4 y3, and among all these you find out the minimum. Okay, among all these distances you find out the minimum distance, that is actually set to the distance between the two clusters. So, the distance between the two clusters is equal to the minimum of all these distances. Complete linkage is actually just the opposite. So, distance here, distance between clusters is equal to the maximum distance between all pairs taken from each cluster. So, basically here again, if you have the same example, you find out the pairwise distances between the entries of the cluster C1 and the cluster C2, and among them you find out the maximum distance, that is said to be the distance between the two clusters. That is what is complete linkage. And the average linkage is nothing but the average distance, average pairwise distance between the two clusters. Okay. So, here distance between clusters is set to the average distance between all pairs taken from each cluster. Okay. So, again in the third case, what you do is you find out the all pairs distances from the entries of x1 to entries of C1 to entries of C2. Now, you find out the average of all these distances, and that is said to be the distance between the cluster C1 and C2. So, these are the 3 different ways in which you can define the notion of similarity or distance between a set of two clusters. Okay. So, using this, now we can envisage to do a clustering. Okay. So, we will take one example of hierarchical clustering, hierarchical agglomerative clustering, and see how it works. So, for instance, let us take this map of Italy here, and we have a bunch of cities. Okay. So, we have a bunch of cities which are separated by some distance in, say, kilometers, okay, from one another. Now, given this matrix of distances, can we find out an agglomerative clustering of the cities based on the notion of closeness of the cities? Okay. So, in order to do so, the steps are as follows. So, first of all, let us say the initial distance matrix is like the following. Between the pairs of cities. So, that is given by the following matrix. Bari, Florence, Milan, Naples, Rome and Turin. Similarly, Bari, Florence, Milan, Naples, Rome and Turin. Now, we can fill in this matrix by the distance between these cities in kilometers. So, as you see, the diagonal should be equal to 0. Okay. So, now Bari from Florence is 662, 877, 255, 412 and 996. 662, 295, 468, 268, 400, 877, 295, 754, 560, 138, 255, 468, 754, 290, 69, 412, 268, 564, 219, 669, 996, 400, 138, 869, 669. So, in this way we have information about the pairwise distance between every pair of cities in Italy, okay, in kilometers. Now, given this input distance matrix, we have to iteratively generate the agglomerative clustering algorithm. Based on the agglomerative clustering algorithm, we have to iteratively generate the communities and using the measure of single linkage. So, if you use the measure of single linkage, then the first two candidates that should actually get merged, okay, the most similar pair, if you see here, the minimum distance is between Milan and Turin. This is 138 kilometers only, okay, which is the smallest. So, the first two nodes that get joined are Milan and Turin. These are the most similar nodes, they get joined in the first iteration. Okay. So, now once they get joined, we can reduce this matrix, we can shrink this matrix, because now Milan and Turin will form one single entity. Okay. They will form one single node in the graph. Okay. So, now with that idea, we can have a revision of the original distance matrix, and we can construct the new distance matrix as follows. Bari, Florence, now Milan and Turin comes together, Naples and Rome. Similarly here, Bari, Florence, Milan and Turin together, Naples and Rome. Again we can fill in the entries of this matrix. Two 55, 412, 662, 295, 468, 268. Now you see from Milan and Turin we have to estimate. So, this is one cluster now, one single node. Now, we have to estimate the distance between this cluster and Bari. So, we find out the distance between Milan and Bari and Turin and Bari, and out of this we put the smallest distance. So, in this case the smallest distance turns out to be 877, since we are using single linkage clustering. So, we put the smallest distance here. Similarly, we find out the distance between Milan and Florence and Turin and Florence, and we put the smallest among this, which is 295 in this case. Similarly, 754 here and 564 here. In this way you construct the matrix in the second iteration. So, if you keep on doing this, you will find that at every step there will be one cluster joining with a node, or two clusters joining based on their similarity using single linkage, or there will be two nodes joining. So, in this way if you keep on merging clusters, at the end if you look at the slides you will get a dendogram like this. Milan and Turin joins first, as we have already seen, then there is Napoli and Rome which joins together with Bari, and then that joins together with Florence, and then this subsegment Milan and Turin joins with the rest. Okay. So, in this way you can construct the hierarchical clustering of this distance matrix. So, this actually gives you an idea of which cities are very close to each other, and this can come handy in making a trip plan. Suppose you are making a vacation to Italy, what are the places you can visit, you can make a nice chalk out of that looking into these clusters. Now, we can now cut the clusters, we can cut this dendogram at different places. So, you can cut here, we will get a different set of clusters. You will get Bari separately, Napoli and Roma separate in a separate cluster, Florence as a separate cluster, and Milan and Turin. So, you can cut at different places like this, like the blue line or the green line or the red line, based on different thresholds, based on different distance thresholds. You can cut this dendogram, and accordingly you will get different sets of clusters. Okay. The granularity of the clusters will depend on what threshold you use for cutting the dendogram. And so, this particular algorithm, as we see, is a bit inefficient, because if you have say n such cities, you will have a n square matrix, and every step you will have to process an order n square matrix, okay, in order to compute the similarities. Now, then if there are n such nodes, you can go in the worst case up to n iterations. So, then the total complexity of the algorithm scales as order of n cube. Every step you have to process n square matrix, and this you have to do at least 10 times, okay, at most 10 times. So, then the worst case complexity would be order of n cube, and imagine if it is a very large graph like a billion node graph, then this kind of an algorithm is very inefficient. Thank you very much.